Okay, good morning, everyone. So today I'm going to take this simulation of Bode and root locus plots. Okay, so this is part of control systems lab activity. Okay, so in your control systems lab, you have two separate experiments. One is Bode plot, and the second one is root locus plot. Bode plot is frequency domain analysis, and root locus is time domain analysis. Okay, and both these plots basically talks about the system stability. So you can check the system stability in frequency domain, or you can check the system stability in time domain. Now root locus, I have already completed two problems in the regular class, so you will find very easy to understand the root locus plots. Okay, on the other hand, Bode plot, though I haven't taught you, okay, eventually I'll teach you maybe after 3 or 4 classes later. But Bode plot is something like magnitude plot versus frequency, and phase angle plot versus frequency. All right, so I'll talk about Bode plot little later. First, let me teach you about the root locus plot. Okay, so are you able to see the window, MATLAB window? Can anyone confirm me?
Sir.
Yeah, fine. Now, what I'm doing over here is that I'm considering the class problem. So in the class, we solved two root locus problems, right? One root locus problem was taking the shape of a circle, correct? And the second one was with a quadratic pole. All right. So the first root locus problem is something like this. Okay. So in the exam, if the lab is conducted in a physical manner, if at all you get any root locus or Bode plot experiment, what you have to do is you have to do theoretical graph, okay, and then you will have to execute in the system. So your theoretical readings should match the MATLAB reading. Okay, if these two readings are matching with each other, you can say that you have successfully executed the experiment. All right, fine. So your transfer function, open loop transfer function, is given as g of s into h of s is equal to k into s plus 2 into s plus 3 divided by s into s plus 1. Okay. So for the given system shown below, determine the stability. Determine the stability. All right. So this is the question. So basically, the same problem we have solved in our regular class, right? The first problem. Okay. Now I hope you have the standard results of this problem ready with you, in the sense breakaway point, etc., etc. Okay. So we have to construct the root locus of this particular open loop transfer function. So how do we do it? So this problem, you have to break it down into numerator and denominator polynomial. Okay, so numerator polynomial, let us take it as num. Okay, and denominator polynomial, let us take it as den. Okay, you can take any value. Okay, any alphabets you can use. All right, so numerator polynomial. Now in order to, in MATLAB, we don't write the equation, we key in the coefficients of the equations, right? So if you expand the numerator polynomial, what do you get? You get a second order equation, right? So s plus 2 into s plus 3. What you have to do is you have to multiply s plus 2 and s plus 3. So what do you get? You get s square plus 5s plus 6 you will get. All right, you will get s square plus 5s plus 6 you will get. Similarly, if you open up the denominator, you would get s square plus s. So denominator poly going to be s square plus s, and to keep the dimension, I'll put the last coefficient as 0. All right. So now that you have the numerator polynomial and denominator polynomial, you can go ahead with Matlab coding. All right. So this is the code which is used in, used to simulate the root locus problem. 1, 2, 3, 4, 5-line code. It's a small code. Okay. So execution is the easiest task actually in Matlab, but you have to carry out the handheld calculation. All right, fine. So numerator, I have taken the numerator as NUM. If you don't want NUM, you can take it as say some P. So P refers to numerator polynomial. What you have to do is you have to just substitute the coefficients. Okay. And this is the syntax. Within a square bracket, you are supposed to place the coefficient. So coefficient of highest powers of s, in the sense descending powers of s, you have to substitute. So coefficient of s square is 1, and coefficient of s to the power 1 is 5, and the coefficient of s to the power 0 is 6. So same thing we have entered here, 1 space 5 space 6. Okay, and put a semicolon. So semicolon, it will not execute this particular line, in the sense it doesn't print the result of the first line. Okay. In the second line, in the beginning I gave denominator, let's say some q, let me take. Okay, so q is equal to coefficients of the denominator polynomial, you have to key in. Okay, so what is it? In the denominator you have a square, so coefficient is 1, followed by s, so coefficient is 1, and you don't have any coefficient there, so you have to put it as 0. Okay, if you don't put it as 0, let's say you just substitute the coefficient of a square and then coefficient of s, Matlab will assume it as something like s plus 1. All right, because Matlab doesn't know whether it is whether an coefficient is missing or not. If you miss out in placing an coefficient, it will simply take it as a first order equation. So you have to be very, very careful. If you have a second order equation in which if an term is missing, you have to take that term as 0. Now it becomes a second order equation, s square plus s plus 0. Okay, done. So we have described the numerator polynomial and denominator polynomial. Okay. Now you have to describe the transfer function. So that's the reason, this code or this line I have written. So transfer function, TF, is the keyword in Matlab. You cannot change it. Okay, it has to be TF. Okay, TF of what? Numerator and denominator. So in place of NUM, I have taken P. So let me write P here. And in place of denominator, I have taken Q. So system, I am calling G of S into H of S as system. If you don't want to write it as system, you can take anything. You can say that, let's say, you can't write transfer function because it is already a keyword in Matlab. Let us say some z. Okay, say some z is equal to transfer function of numerator and denominator, which is p comma q. Okay, so this is the keyword, and then you have the keyword called root locus. So this keyword basically plots the root locus plot. So root locus of what? Root locus of the given transfer function, which we have taken it as z. Okay, and then grid, this is optional. This grid command is optional. So what happens is that if you place grid, you will get what you say, a proper graph. x and y axis can be easily traced. Okay, without grid you will get a plain sheet of output. All right, so this is my MATLAB code, okay, for root locus. Quickly to wrap up, enter numerator polynomial coefficient, enter denominator polynomial coefficient, construct a transfer function by typing transfer function of numerator comma denominator, that is p comma q, and then execute the root locus plot by writing this particular command, root locus of the given system, that is z. Okay, all right, now you save. Okay, I have already saved, so what I will do, I will save it as a different file. Okay, so let me save this as root locus underscore 2. Okay, and it gives the option as .m. Automatically it saves, okay, in .m. So .m is the file extension for MATLAB code. Okay, then save. So the file gets saved. Okay. And over here, let us execute F5 or run command I can press. Okay, and this is what I get, the root locus graph, right? Now in the root locus graph, so class alidini sir, class alidini sir, 10 minutes. So what you have to do is you have to correlate the system plot with the plot which we had drawn, in the regular class, right? In the regular class, we had got a circular plot. Even in the system, we are getting a circular plot, and you can see the locations of poles and zeros. So you have a pole at origin, right? And you have a pole at -1, right? Because poles we are projecting with the symbol X, and zeros are projected with the symbol O. So 1, 0 is located at -2, and the other 0 is located at -3. Okay, and this is your j omega axis, and this is your real axis. Okay. Now, in the regular class, what did we get the breakaway point as? We got the breakaway point as -0.633 and -2.366. So this is your first breakaway point, and this is your second breakaway point. Okay, so you can probably zoom in. Okay. Okay, all right, no issues. So okay, just roughly I have placed, you can see, right, the pole value. Pole value is on the real axis -0.634. -0.634. Okay, my point is not exactly on the real axis. Okay, because manually I have placed, right? So that's the reason it is showing a small imaginary value. If I were to be keeping my point exactly on the real axis, I would have got my imaginary part as 0. Doesn't matter. Okay, so you can clearly observe that the breakaway point is -0.634. That is what we got in our theoretical calculation. Similarly, let us try to locate the second breaking point. Okay, that is somewhere here. So what you have to do is you have to place the cursor on this particular point, and then you press right click. Right. So the second breakaway point is -2.37, and in the handheld calculation we got the second breakaway point at -2.36. Okay, so it is agreeing with the theoretical results. Okay, so this is how you can plot the root locus plots. Okay, so in your exam what you have to do is you have to show the breakaway breaking points. Okay, and if there are any k marginal value or intersection with the j omega axis, you can show that as well. All right. So that completes the first problem. Okay. Very simple problem basically. Okay. Next, let us go to slightly, a complex one. Okay. That is problem number 2. Okay. So in problem number 2, okay, this also we have done it in the class. We shall take g of s into h of s is equal to, yeah, what did we take? K divided by s into s plus 3. S into s plus 3 into s square plus 2s plus 2. S square plus 2s plus 2. Okay, so this is our given system whose root locus plot we are supposed to find out. So this problem also we have solved in the class. Okay, so this is a good problem, I would say, because so many things we can cross check. We can cross check the break-in points, breakaway points, k margin, intersection with j omega axis, etc., etc. All right, fine. So let's go ahead with the problem. Now, in the numerator, what do we have? We have k, right? That means to say we don't have any polynomial of s. So what you can do, you can take p as 0 space 1. I'm just trying out 0 space 1. So 0s plus 1 it takes, right? We are taking k as 1. 0 space 1 you can take. And in the denominator, okay, so denominator is quite big, right? S into s plus 3 into s square plus 2s plus 2. So what we can do, we can make use of convolution theorem here. So what we can do is first we will multiply these two. Okay. So when we multiply these two, what do we get? We get s square plus 3s. So let me take q as a part of the denominator, s square plus 3s plus 0. And the second function, second part of the denominator, let us take the quadratic equation whose coefficients we are supposed to key in 1 space 2 space 2. All right, enter. So what do we have? We have two polynomials of s. First polynomial is s square plus 3, and the second polynomial is s square plus 2s plus 2. And we need to multiply these two polynomials in order to get the denominator, right? So what we can do is, probably you can use the code something like denominator is equal to convolution of I think q comma r, q into r, okay. And then we can frame our transfer function something like, let's say system is equal to transfer function of numerator. Okay, what did we name the numerator as? P, right? And what is our denominator? The ultimate denominator is den, right? Because we have multiplied q with r through convolution. So it is r, sorry, denominator den, and root locus of system. So we'll save it as a different file. Let's say 3. Okay. We'll save. Now we'll execute. Okay. It is throwing some error, incorrect dimensions in matrix multiplication. Okay, because I don't remember the code, or I can quickly factorize this. So I have s square plus 3s into s square plus 2s plus 2. So if I multiply s to the power 4 plus 2s cube plus 2s square plus 2s cube plus 6s square plus 6s. All right, so if I multiply these two manually, we'll get Q as fourth order equation basically, whose coefficients are S1 plus 5, that is 5s cube, plus 8s square, so 8 plus 6s, that is 6, and 0. Okay. What I've done, I've just multiplied the two factors, okay, because it was throwing me some error with the convolution. Now let me save it. All right. It takes some time to draw the plot. Okay, I think it has plotted. Yeah, right. So this is the root locus plot. Okay. Now, can you correlate with the plot which we drew manually? Right. So there are 4 open loop poles, right? One pole is located at 0. The second real pole is located at -3. And 2 complex conjugate poles, right? -1 plus or minus J1. So these 2 are complex conjugate poles. All right. And we got 1 breakaway point. Okay, I mean, we got 3 breakaway points and only 1 was found to be valid or legit. So what you can do, you can even cross-check the breakaway point value. So place the cursor at the breakaway point and just click, right click. Okay. So what do we get? The breakaway point value as -2.3. Okay. If I check the breakaway point value with the theoretical calculation, yeah, it is agreed. So theoretically, we got -2.3, and the same value the Matlab is also showing. Okay. All right. So that's the breakaway point. Now, the angle of asymptotes. Okay. Because the Matlab never plots the asymptotes, okay, because Matlab has all those logic built in within that R locus function. Okay, so this is one branch of the root locus which is moving towards infinity. Similarly, the other branch, will also be moving towards infinity. Okay, so that's about the root which is located at -3 and the root which is located at 0. Okay. Now the remaining 2 roots which are complex conjugate. Okay. So the first root which is found in quadrant 2 is basically moving tangentially with respect to the angle of departure. Okay. And then it cuts the j omega axis at a distinct point, and then it moves towards infinity. Okay. Similarly, the mirror image of complex pole will appear in quadrant 3, right? So what you have in quadrant 2 will be there in quadrant 3 and quadrant 4. That's because root locus is always symmetrical about real axis. All right. Now we want to see what is that marginal value of k, that gives the marginal stability. So somewhere here, the root locus plot cuts the j omega axis, right? So place the cursor and press right click. Okay. So what is that gain you are getting? K. So this k refers to k marginal. Okay. So let's see in our theoretical calculation. What did we get the k marginal value as? Okay. K marginal, we got it as 8.16. And here we are getting it as 8 we are getting. That's okay. That's because manually I'm placing the point. So it is agreeing with the marginal value of k. All right. And at k marginal, what are the roots of auxiliary equation? Theoretically, we found the roots of the auxiliary equation as plus or minus j 1.095. Okay, so let's see what do we get the root value at k marginal. Okay, can you see the pole value here? Okay, so pole value is plus 1.09i. Okay, if you see the real part, it is negligibly small. It is 0.006. That is, close to zero itself, right? So at k marginal, your roots are purely imaginary. Okay, so one root is in second quadrant, hence with a positive sign, right? Now, if you want to locate the negative root, somewhere here. Okay, so wrongly I located. So let me press it exactly at that particular location. Yeah, right. You can see the root value minus 1.09i. Okay. And it also gives the overshoot. How much is the overshoot? 97.8%. That means to say 100% overshoot. So that is what is expected in case of a critically stable system, right? All right. So that's your root locus plot. And when it comes to stability, how do you conclude? So if the value of k is less than k marginal but greater than 0, all the four roots are found in LHS of the S-plane. When k value is set exactly at k marginal value, the two roots are found on the imaginary axis. And if k value is increased beyond k marginal, which is 8.16 with respect to this particular problem, what happens? The two roots starts leaking into the right hand side of the S-plane, and thereby the system becomes unstable. So for stability, the value of k or range of k should be greater than 0 but less than k marginal. For critically stable system or marginally stable system, k value should be at k marginal value. And for an unstable system, k should be out of the k range. Okay, that is greater than 8.16. Okay, so that completes the root locus problems. Okay, now you can try out with the different problems. Okay, so what you have to do is you have to carry out handheld calculation, and then you execute in your system, and then you correlate the theoretical results with the system results. All right. Okay, so that completes root locus problem. Bode plot, little later I will record and I will post it in the class group. Okay, because I need to leave for urgent work. All right, so that's it for root locus.